Okay, so in the last video we started talking about traveling waves, and the last thing we talked about in the previous video was about the different types of traveling wave graphs. Okay, and so just to recap, there's two types of graphs we can use to visually represent a traveling wave. Okay, we have either a displacement distance graph or a displacement time graph, and you can usually identify these pretty easily. Either they'll be explicitly labeled in the problem, or if you look on the y-axis and the x-axis, you can obviously tell if it's a distance displacement time graph, or sorry, a displacement time graph or a displacement distance graph. Okay, so the difference is that a displacement distance graph is a graph which basically shows you one instant in time, but it shows you the entire waveform. Okay, and what you can do from this type of graph is you can measure the distance from one point on a graph to the next successive point to determine the wavelength, which we talked about in the last video. Okay, and remember the symbol for wavelength is lambda, that's that upside down looking y thing. Wavelength, the SI unit for wavelength is the meter. That's often expressed in other units of length, so do pay attention to that and make sure that the units are correct. Now, displacement time graph, rather than looking at the entire graph at one point in time, a displacement time graph basically picks one point that, of all the particles making up the wave, it picks one particle and it follows that particle along over time. Okay, and remember that when talking about a traveling wave, you can think of a traveling wave as being created by basically a bunch of particles, each one in simple harmonic motion, but with a slight phase difference compared to the one next to it. Okay, so on a displacement time graph, you can use the distance between one point on the graph to the next successive point to measure the period. Remember, period is that capital T. That's the time for one complete oscillation. So definitely make sure you know what type of graph you're looking at. If you're given a motion graph, and make sure you pay attention to the units. So what we're going to do now is we're going to do a few example problems with this before we start talking about electromagnetic waves. Okay, so I'm going to make this bigger. Okay, so here is an example problem, and it says that graph 1 shows the variation with time t of the displacement d of a traveling wave. Graph 2 shows a variation with the distance x along the same wave of its displacement d. Okay, so in other words, the top graph is a displacement time graph, and the bottom one is a displacement distance graph. Okay, but they represent the same wave. Notice, by the way, that because on the y-axis we have the displacement of the wave itself, on both graphs that represents the amplitude. Okay, so the first question says, use the graphs to determine the amplitude of the wave motion. Now remember that amplitude is defined as the maximum distance from equilibrium. Okay, and amplitude is never a negative number, it's always a positive number. Okay, unlike displacement. Some people get confused between amplitude and displacement. So remember, amplitude is typically, for a wave like this, amplitude is a constant. It is always a positive value, whereas displacement is basically what's being measured on the y-axis. Okay, so looking at this graph, we can see that the displacement value can have any value between 4 and -4. Okay, the amplitude is just one single value. That's not a function of time. So we can see pretty clearly that the amplitude here is 4. Pay attention to the units, because if you look at the y-axis, the label says that this is measured in millimeters, so that would be 4 millimeters, would be the amplitude. Okay, and so depending on how the question was worded, you might need to convert that to meters. If it doesn't say you need to convert, then you'd probably be okay with 4 millimeters, but do be very aware of the units on your graphs. Okay, so 4 millimeters, 0.004 meters, either of those would be acceptable. Okay, so the next question says, use the graphs to determine the wavelength. Okay, so there's two types of graphs. One of them can help you find wavelength and one of them cannot. And it's pretty easy to remember because one has time on the x-axis and the other has units of length or distance on the x-axis. So wavelength, think units of length. Okay, so we're going to use graph 2. That's the displacement distance graph. And basically you pick any point on the wave. So in this case I'll pick the starting point, but it could be any point, and you measure the horizontal distance until that same point repeats itself. Now, when I say that, I don't mean this point right here, okay? Because even though this point is also going through 0, here the graph is going down, whereas at the start the graph was going up. So I have to go one complete back and forth, and then that horizontal distance is one wavelength. And so I would say the wavelength is equal to 2.4 centimeters. I believe there's decimals in there. Okay, so 2.4 centimeters. Okay, now again, pay attention to the units, because if we had to do a calculation with that, we may need to convert that to meters, to SI units, because normally you do calculations in SI units. Okay, so C, use the graphs to determine the period. So this is going to be with the displacement time graph, and the way you measure it is the exact same way, but again, pay close attention to the units. Okay, so you pick a point on the graph. Again, doesn't really matter which one, so I'm just going to start at the beginning, and I measure the time now, not distance, but time, until the wave repeats itself. So one full back and forth, and that gets me to here, and so the period would be 0.3. Pay attention to the units. In this case, it's measured in seconds. And make sure you don't confuse a lowercase t, which is time, with period, which is an uppercase T. The difference is that time can basically be any value, whereas period is one specific value. Okay, kind of like the difference between amplitude and displacement. All right, and then one more question, use the graphs to find the frequency. Once we find the period, we automatically have the frequency, because the period is 0.3 seconds, and frequency is 1 over the period. And so that would be 1 divided by 0.3, which would be 3.3 hertz. You remember that the unit for frequency is hertz. Now, if this time was not in seconds, let's say if it was in, some other unit, then you would have to convert that to seconds in order to do this frequency calculation. Because hertz, if you break hertz down, hertz has units of 1 over seconds. Okay, and so the period has to be in seconds in order for this to give you the frequency in hertz. Alright, so and then finally use the graphs to find the wave speed. We talked about the wave equation in the last unit. V equals lambda times F. Okay, so now that we have the wavelength, all we have to do is plug those values in. And so that would be 2.4 times the frequency of 3.3 hertz. Notice, by the way, I'm plugging in 2.4, but that's 2.4 centimeters from the graph. So that means my wave speed would come out in centimeters per second, which is fine, but you have to include the unit, because lots of times they will not give you credit for these types of questions if you don't have the correct unit. Now, if you converted from centimeters to meters, let's say you had 0.024 meters and you multiplied by the 3.3 hertz, then the wave speed would be in meters per second. Okay, so again, just make sure that you're being consistent with your units. The IB does not typically take off points for units, but on questions where they do it, it's very often from this topic, the wave topic. Okay. Notice here that they actually did the calculation, just dividing the wavelength by the period, and that would also be fine. Okay, so just a very, very basic example using different types of traveling wave graphs. Okay, so pause it there if you need to look at that. And then just a few more. We have another two-graph situation here. Use the graphs to determine the amplitude and wavelength of the wave motion. So see if you can use these graphs to find the answer to this question. So look at these two graphs and use them to find the amplitude and the wavelength of the wave motion. Okay, so hopefully you included units. The amplitude is 2 millimeters, and the wavelength using graph number 2. Okay, if you measure from one point to the next successive point, is 0.3 centimeters, which is 0.003 meters. And either of those would be fine as long as you include the units. By the way, I don't know why they put y here for wavelength. It should be a lambda. Okay, use the graphs to determine the period and frequency. Again, try to do this one on your own, paying attention to the units. Okay, so hopefully you use graph number 1. Hopefully you notice that graph number 1 is given to you in milliseconds. And so if you look at the graph, you can see that the period appears to be 0.25 milliseconds, okay, which if you convert to seconds, you divide by 1,000, you get 0.00025 seconds. And then frequency is just 1 divided by that. Okay, so always put your units on these answers. Okay, C, use the graphs to determine the wave speeds. Try to do this one on your own. Okay, and just a very basic calculation, you should have got 12 meters per second, assuming you convert to SI units. And again, I think this is a situation where as long as the units were correct, if the question didn't specify the units for your answer, I think the IB would accept anything as long as it was correct. Okay, but do pay attention to the units. Okay, so I'm going to skip past some of these examples and let's talk about electromagnetic waves. Okay, so electromagnetic waves, this is the last little bit in 4.2. So in the last video we talked about the difference between mechanical waves, which are waves which require a medium to travel through, and electromagnetic waves which do not. Okay, and we'll talk more about what actually an electromagnetic wave is later, but electromagnetic waves is the only type of wave that exists that does not require a medium to travel through. Now, just to clarify, electromagnetic waves can travel through a medium. Anytime you see anything, you're seeing with light that is obviously traveling through the air in the room. Okay, you can see underwater, so light can travel underwater. Okay, electromagnetic waves can travel through media, but they do not require a medium. Okay, and so even in the vacuum of space, electromagnetic waves can move. And again, we'll talk more about what an electromagnetic wave is later, but basically, electromagnetic wave, as the name implies, has basically an electric component and a magnetic component, and they kind of feed on each other, and that allows the wave to self-propagate through space without a medium. Something you should know, all electromagnetic waves, regardless of where they are on the EM spectrum, regardless of the frequency or wavelength, travel at the same speed in a vacuum. That in a vacuum part, by the way, is important in a vacuum because we'll see in the next unit later when we talk about refraction and indices of refraction that when electromagnetic waves travel into different media, the wave speed actually changes. Okay, in a vacuum though, all EM waves travel at the same speed, and we give this constant a name. We call that a c. That's the same c from E equals mc squared, and the value for that is approximately 3 times 10 to the 8 meters per second, which is very, 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 very fast. Okay, it's like 300,000 kilometers per second. Okay, you also might be aware that electromagnetic waves exist across a wide spectrum. This is called the electromagnetic spectrum or the EM spectrum, and different parts of the spectrum have different properties, as we'll see over the next few minutes. Okay, I will also tell you that the speed of light, that value is given to the data booklet. This is a picture of the IB data booklet, and you can see it's on the constant page down here, speed of light in a vacuum. Okay, along with some other useful constants. Okay, so obviously we are all familiar with light, but light actually makes up just a very, 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 very small part of the electromagnetic spectrum. And actually I'm going to stop that because the noise kind of bugs me. Okay, so this is the whole EM spectrum, and it ranges from radio waves to gamma rays. You can tell from the picture on the screen that radio waves tend to have the highest wavelength out of the EM spectrum, whereas gamma rays tend to have the shortest wavelength. You can look at that visually and tell that. As far as frequency goes, because wavelength and frequency are kind of inversely related to each other, radio waves tend to have the lowest frequency, whereas gamma rays tend to have the highest frequency. Now, what we human beings can see with our eyes, and some animals can see different parts of the EM spectrum better than others, but what we can see with our eyes is only a very tiny fraction of the entire EM spectrum. Humans can see somewhere between approximately 700 to 400 nanometers. Okay, now this is important, so make sure you add this to your notes. The wavelength of red light is approximately equal to 700 nanometers. And that's a very useful number just to know as a reference. And because sometimes you'll have questions where just knowing a few numbers can help you answer some questions. I don't expect you to know every single one of these numbers, but you at least need to understand the order of the EM spectrum, and you need to be able to guesstimate some different values. Okay, so I'm giving you some reference values now. The wavelength of blue light is approximately 400 nanometers. Now, every year I tell people that, and for some reason people seem to think, oh, that means wavelength should be measured in nanometers. No, wavelength is measured in meters. That's the SI unit for wavelength. It just so happens that the light that we are familiar with, red, between red and blue you have the whole rainbow. It just so happens that those wavelengths tend to be in the hundreds of nanometers. There's nothing special about nanometers. It's just happens to be the wavelength of visible light. Okay, so in doing calculations, you need to make sure that wavelength is measured in meters, not nanometers. Okay, but I will remind you that nano is a SI prefix that is 10 to the minus 9. Okay, so that means the wavelength of red light, for example, that's 700 nanometers. That's the same as 700 times 10 to the minus 9 meters. Or you could also say 7 times 10 to the negative 7 meters, if you wanted to convert that to strict scientific notation. Okay, so just some reference numbers for you to keep in the back of your mind. Now, we're very briefly going to go through each part of the EM spectrum, but definitely make sure you have this added to your notes. Okay, so gamma rays. Okay, so gamma particles are high energy photons, and we talked about that in the context of like radioactivity. But gamma rays can be produced in lots of different situations where you have very, very, very energetic photons that have an enormous amount of energy. One way that could happen is radioactivity. What you're looking at now is basically a picture of the sky, I guess, but it's taken not with invisible light, but it's actually taken in terms of gamma rays. And so the bright lights you're seeing are basically the night sky with the bright spots representing gamma photons, really high energy photons. And so in space, there's lots of different ways that gamma rays can be produced. For example, you have pulsars, which are really, really fast spinning neutron stars. You have quasars, which is basically when you have a really supermassive black hole and you have gas going into the black hole, and it releases a ton of energy, and that energy comes out in the form of those super high energy photons, those gamma photons. You could also have just random particles colliding with each other in space for whatever reason, and causing pair production of super high energy photons. So there's lots of situations throughout the universe besides radioactivity where gamma rays can be produced. And if you're interested, you can look on Wikipedia or something about gamma rays. But gamma rays are just really, really high energy photons. Okay, in fact, the next part of the EM spectrum is X-rays. The only difference between a gamma ray and an X-ray is gamma ray has more energy. That's basically it. I mean, a supercharged X-ray is a gamma ray. And we all know what X-rays are for. X-rays, if you break a bone, you go and get X-rayed because those particles, because of their wavelength and their composition, can go through your skin, and they can be used to for medical purposes or whatnot. Okay, very, very short wavelength, about 10 nanometers. Next, we have ultraviolet. Okay, or what you call UV. And you see these in lots of different applications and areas. Black lights, if you ever go to a party and you see, people's clothing glowing, like at a rave or something, that's usually caused by a black light. Tanning booths are usually use ultraviolet radiation to give people tanning. And then, of course, the sun emits ultraviolet radiation, which is why we wear sunscreen. Because something that you should know about ultraviolet radiation is that parts of the UV spectrum are ionizing. Okay, and just to remind you, radiation that's ionizing, and by the way, gamma and X-rays are also ionizing. But ionizing radiation basically has enough energy to remove electrons from atoms, which can be very dangerous to your health because that can cause, your DNA to be damaged, your cells to be damaged. And so that's one reason we put sunscreen on, is to protect ourselves from that. I always thought it was strange that people go to tanning salons and they pay a lot of money to get hit by this ionizing radiation, which seems kind of silly to me, but that's just my opinion. So that is ultraviolet radiation. And by the way, X-rays and gamma rays are also ionizing, of course. That's why when you go to the doctor, you go to the dentist, they make you put like a lead vest over yourself before they do the X-rays to protect the rest of your body from that ionizing radiation. Okay, visible light, of course, we all know what visible light is. That's what we can see with our eyes. Some animals can see in the ultraviolet part of the spectrum. Some animals can see in the infrared, but we basically can only see between, like I said, about 400 to 700 nanometers. And some textbooks have those values a little bit different. Those are only approximate values. I've seen some textbooks say anywhere from 350 to 850 nanometers, but we can only see a very small part of the EM spectrum, everything between red and violet. Now, infrared photons we typically associate with heat. These are photons that have less energy than visible light. Visible light is not ionizing. Infrared is also not ionizing. In fact, in terms of photon energy, we're kind of going backwards from highest to lowest. And so gamma, X-rays, and ultraviolet all include ionizing radiation, or ionizing photons, ionizing particles of light. Where visible light is non-ionizing, and so is infrared. Again, so you see infrared everywhere from, heat. When we talk about people giving off heat, that's not heat that you can see with your eyes, but they give off these infrared photons that you can see with thermal imaging. Most TV remotes, if you look at the end of the TV remote, you can see it's got like a little light bulb that you cannot see with your eyes, but that little light bulb is emitting infrared radiation. Okay, if you ever want to do something for fun, just to be able to see that light bulb go off, I know it works at least on my iPhone. It may or may not work on your phone, but if you turn on your selfie camera and you hold up your TV remote to the selfie camera and you press the buttons on the remote, you'll actually see the end of the remote. You'll see that little light bulb blink, because for some reason your infrared selfie, your selfie camera on your phone, not always the front camera, but the selfie camera can see into the infrared part of the spectrum. Okay, so test it out. It may or may not work with your phone, but it definitely works with mine. And I can see that the little light bulb at the end of my projector remote flashing in my selfie cam. Next on the EM spectrum is microwaves. Microwaves are used from everywhere from radar to cooking food. Obviously, we're all familiar with microwaves. The wavelength of microwaves tends to be pretty short. Obviously, enough to fit a couple wavelengths inside that little box that you have in your kitchen. Somewhere around the order of magnitude of 1 centimeter. Here you can see on this diagram that the wavelength is more like 12 centimeters or 13 centimeters, but that's just like rough estimates. Okay, also I want to point out that, remember, part of ultraviolet is ionizing. Visible light is not at all. Infrared is not at all. Microwaves are not at all either. Okay, in fact, they're pretty far away from ionizing. And so, to all the people out there worried about getting, if you stand too close to your microwave, you'll get cancer. That's not a thing. Okay, microwaves are non-ionizing radiation. Those photons just don't have the energy to cause cancer. I know everybody's mom tells them don't stand too close to the microwave or you'll get cancer, but that's definitely not a thing. Okay, same thing with cell phones. Radiation from cell phones just doesn't really have enough energy to cause, as far as we know, to cause those kind of issues. And the last part of the EM spectrum, you've got radio waves, which obviously we use for like wireless data transfer to listening to the radio. Now, if you think of the EM spectrum, we block out big chunks of the EM spectrum to use it for different things. Okay, so just to give you an idea, if you have like an alarm system, or if you have like a garage door opener where you press a button and your garage door opens up, okay, we use about 40 megahertz, that part of the spectrum, somewhere around 40 megahertz for those devices. Baby monitors, around 49 megahertz. Radio-controlled cars, somewhere between 27 and 75 megahertz. And so we have different parts of the EM spectrum blocked out for different applications. And the idea is that we do this so that they don't necessarily, well, number one, so they don't necessarily interfere with each other. And number two, depending on what the frequency is, that affects the wavelength, and that affects how far the signals can travel and whatnot. Okay, Wi-Fi, Bluetooth operates on a frequency of about 2.4 gigahertz, which is quite high. Okay, that's close to the same range as microwave ovens. Okay, and so we use different parts of the EM spectrum for different applications. Now, you don't need to know any specific values other than red light and blue light, but you should be able to name the different parts of the EM spectrum in order from starting at the longest wavelength going to the shortest wavelength. Okay, so looking at this diagram, I want you to fill in the parts of the EM spectrum using the knowledge that we just talked about. Okay, so fill in A, B, C, D, E, F, and G with the different parts of the EM spectrum. Okay, and not that you need to use this equation for this unit, but I do want to remind you that the energy of a photon is given by the equation E equals hf, Planck's constant, times the frequency, which basically means that photons with a higher frequency have a higher energy. Okay, which is why the parts of the EM spectrum with the highest frequency have the most energy and therefore tend to be ionizing and therefore harmful to humans. Okay, so we are almost done with this video. I just want to go, well, I guess we can go ahead and stop here for now. In the next video, we'll do a few more examples as far as the electromagnetic spectrum is concerned, and then we will talk about wave intensity, and we'll start getting into 4.3. I also want to remind you that this unit, we're basically testing over 4.1, 4.2, and 4.3, and so we'll start 4.3 in the next video. And I would say the hardest stuff in this unit, not that super hard, but the hardest stuff in this unit is definitely in 4.3, which I believe is wave characteristics. So make sure you're keeping up with your worksheet and you're reading your IB physics textbook. As always, please let me know if you have any questions, and I'll see you guys in the next video.